So there are two types of rotations of the plane of polarized light. The plane of polarized light can either be rotated for a chiral molecule either to the right or to the left. And we represent those whenever we are writing down the specific rotation by the sign. So the rotation of the plane of polarized light to the right or clockwise is expressed by either a positive sign or a small d. D means dextrorotatory, and this means that the plane of polarized light is rotated to the right. On the other hand, the rotation of the plane of polarized light, if it is to the left, then this is counterclockwise. And it is represented by either a negative sign or a small l, which is a levorotatory, something like that. See, this is the name. It's included in the name, but there is no way for you to know the plus and the negative sign, as we said before, unless you go ahead and you perform the actual experiment using the polarimeter. You put your sample in and see what sign you get for the observed rotation, and then you calculate your specific rotation in there. But this positive and negative sign, these are part of the name. And when you see them, you need to understand what do they mean. So a positive sign here means that this molecule is an optically active molecule and it's capable of rotating the plane of polarized light to the right. This one, on the other hand, it's its mirror image. So it's capable of rotating the plane of polarized light to the left. Always, mirror images, they do rotate the plane of polarized light to the same degree. Notice that the angle is exactly the same. So this molecule rotates the plane of polarized light 2.6 degrees, but it is to the right. And its mirror image, because here I do have a mirror image of that molecule. This is a mirror. It's a mirror image because I can easily see that I'm seeing a reflection there. Hydrogen stays behind, the OH is in front, and the CH3 and the acid are in plane. So its image will rotate the plane of polarized light at the same angle, 2.6, but it's going to be in opposite direction. So it's going to be a negative sign, which is a levorotatory, or it can rotate it to the left. So D and L, these are called relative configurations. And these configurations, as we said, we cannot figure those out unless we run the experiment using the polarimeter in there. The second type of rotation is the rotation around the chiral center. Now, this one, you don't need a polarimeter or any instrument to measure. This one is called absolute configuration, and you measure that based on the groups that are around the chiral center. This is called the Cahen-Ingold rule, and the rotation here, absolute configuration, is two types. It's either you can rotate the chiral center clockwise or you can rotate it counterclockwise. The rotation, as we said, it's based upon the groups that are around the chiral center. So let's have an example in there. First of all, you would need to locate your chiral center. And by definition, a chiral center is a center that is surrounded by four different groups in there. Now, after you locate the chiral center, then you would need to determine the priority of the groups around the chiral center. The priority is based on either the atomic number or the atomic mass, whatever you want to go with, but you have to move one element at a time. Let's have this simple example first. Locate your chiral center. After you locate your chiral center, check the connectivity of every element, not a group, element that is connected to the chiral center. So here I do have a carbon, not a CH3. You move one element at a time. So a carbon, I have a bromine, I have a hydrogen, and I have a fluorine in there. And then you go ahead and you arrange the atoms based on either the atomic number or the mass number. it really doesn't matter. I'm going to go with the atomic number in there. So the one that has the highest atomic number, we're going to go ahead and give it number one. So you arrange from the highest mass number to the lowest mass number. Bromine has the highest mass number compared to fluorine and carbon. The second one is the fluorine. This is the second mass number. And then you have the carbon. This is the third. And then the hydrogen is going to be the fourth. Now, the rule for determining the rotation around the chiral center is that the lowest priority group, so bromine is going to be the highest priority group. The lowest priority group needs always to be behind. This is always the rule in there. And here, my lowest priority group is behind. So the hydrogen here is behind. So the way that I do the rotation around groups 1, 2, and 3. And notice how am I going with the rotation? 1, 2, and 3 like that. And this is a clockwise. I'm going a clockwise with the clock. Then the rotation around the chiral center has an absolute configuration of R. Let's have another example, okay? Something like this. So the first thing that you do is, again, you go one element at a time. First of all, you need to locate your chiral center. So this is going to be my chiral center over here. Let's go ahead and put an asterisk because the rotation, the absolute configuration is always around the chiral center. So you would need to have a chiral center in there. So let's locate that. This is my chiral center, and then the groups around the chiral center. So I have a carbon, okay, or elements around the chiral center. I have a carbon, I have an oxygen, I have a bromine, and I have a hydrogen in there. Okay, so now I need to arrange those atoms based on the atomic number. The one that has the highest atomic number is the one that is going to be the higher priority. So I'm going to give it number one. Bromine has a higher atomic number than oxygen, than carbon, than the hydrogen. Now, if you've noticed here that the lowest priority group is not behind, just going to copy the same example over here. So this is the same example. And this is the case wherever you don't have your lowest priority group behind. So this is what you do over here. You look for the group that is behind. And the group that is behind here is the bromine. And you look for the group that is the lowest priority. And you go ahead and you switch them. So here, draw your molecule, and it's going to be a CH3 and OH. Now here you're going to end up having your hydrogen behind, and here you're going to end up having your bromine in there. So see, you switch them so that your lowest priority group is behind, because you cannot do the absolute configuration of the chiral center unless your group number 4, which is the lowest priority group, is behind. So you switch those two groups over here. And the reason why I chose this one, because this is the behind, and I want my hydrogen to be in its place. And now you go ahead and you do your configuration around the chiral center. You arrange the groups based on the higher atomic number or mass number. Bromine comes first, then the oxygen. We mentioned that you go one element at a time. So you look at the oxygen, not the OH, the oxygen. And then you look at the carbon in here. This is going to be 3. Neglect the hydrogen, and you're moving by 1, 2, and 3. So the configuration here, after the switching, the configuration is an S configuration. It's counterclockwise, it's an S. Because you did the switch, you're going to go ahead and invert. And in reality, the configuration now is an R configuration. So always you switch, you do the configuration, and then whatever configuration you have, you invert it. Invert it meaning that you choose its opposite. It's R, so now the absolute configuration of this chiral center here is an R configuration and not an S configuration. Let's have another example. Now, here in this other example, as I said, we're going to locate always the chiral center, which is the center that has 4 different groups around it. It needs to be an sp3 hybridization. Let's go ahead and highlight that. And then look at the elements that are connected to the chiral center and move one element at a time. If you have a tie, then you're going to move to the next element. So here's how you do it. This chiral center is connected to a carbon, and a carbon, and a carbon. All of these are a tie because all of them are carbons. So now I'm going to go ahead and look at the next element in there. So notice here I did not consider this whole group all at once and said that this is 4 carbons, this is 3 carbons, this is 2 carbons, then definitely this one is going to be the higher priority because it has the higher atomic number. No. Or higher mass number in this case. No. You go one element at a time. So all of these carbons are a tie. Then you move on to the next carbon. So here I do have another carbon connected, another carbon connected, and another carbon connected. Here I do have a hydrogen. So definitely this one is going to be the lowest priority. I give it 4. And then all of those are a tie. Now I'm going to go ahead and move to the next element in here. So here I do have a carbon and a carbon. These two are going to be a tie. This one is connected to a carbon-carbon. This one is connected to a carbon-hydrogen. So definitely this is going to be the highest priority. This is the second. This is going to be the third. And this is going to be the fourth. Okay. Now notice that the second priority is behind and the fourth priority is in plane. So what we're going to do over here is we are going to switch the second priority with the fourth priority as we did before. So simply switch the second priority with the fourth priority. So the second priority now is going to be here. And the fourth priority is going to be behind because I need always my fourth priority to be behind. Once you do this, go ahead and do your configuration around the chiral center. This is 1, 2, and 3. This is in reality, it is S, but in reality, since you did the switch, it's going to be R. So the original structure is an R configuration and not an S configuration. And this is why you go ahead and you put R over here, which is the absolute configuration of this chiral center. Now let's say if I have complex groups around the chiral center, like for example, a carboxylic acid and an aldehyde, and I want to know which one is a higher priority in there. By looking at the carboxylic acid is the COOH, and this is abbreviated as a carbonyl connected to the OH. The aldehyde, on the other hand, is a CHO, and this is represented by a carbon double bond O that is connected to a hydrogen. So you got to know, what is this carbon double bond O in here? What does it mean? The carbon double bond O is, in reality, is the same as the carbon connected to 2 oxygens and an oxygen connected to 2 carbons. So if you have a carbonyl the carbon double bond O, a double means two. So this carbon needs to be connected to two oxygens. So this is the carbon here. This carbon is connected to two oxygens. So this is one oxygen. This is a second oxygen in there. And then this oxygen is connected to two carbons. This is one carbon and this is another carbon. So every time you see a carbonyl, carbonyl means this. So let's go ahead and figure out the priority around the chiral center in there. And as I said, we're going to move one element at a time. I'm going to go ahead and write the backbone of the structure here. So we have our carbon, and that carbon is connected to an oxygen in there. Next to the oxygen, there is a hydrogen. But I'm going to go one element at a time. So I have an oxygen here. In plane, I do have a carbon. That carbon is connected to two hydrogens. And then I have another carbon that is connected to two hydrogens. And then I have a carbon that is connected to three hydrogens. I need first to look at the first carbon in there. If there is a tie, then I would look at the second carbon that is connected to it. In plane, I do have my carboxylic acid. So the carboxylic acid, as we mentioned, it's a carbon double bond O that is connected to the OH. So let's draw first the carbon double bond O in this structure here, which is a carbon that is connected to two oxygens. So we're going to have the two oxygens in there, and an oxygen that is connected to two carbons. But on this carbon here, don't forget, on this carbon here, which is basically this one, I do have also the OH. So I would need also to put the OH. You can put it anywhere you want in there. Okay, so this is going to be the carboxylic acid. This is how it looks like. Now for the aldehyde is in front. Let's keep it in front in there. And then we have the carbonyl. So we're going to write it exactly as we see it. The carbon connected to two oxygens, and the oxygen is connected to two carbons. But now on this carbon, I do have a hydrogen in there. Now, after I do this, I'm going to go one element at a time. So my chiral center here is connected to an oxygen, to a carbon, to another carbon here, and to another carbon there. So you can easily see that the oxygen is the highest priority among all the carbons. So this is going to be priority number one, because it has the highest atomic number. Now I'm going to go carbon connected to an oxygen, carbon connected to an oxygen, carbon connected to a carbon. This is going to be the lowest priority, so this is going to be priority number 4 in there. Now between those two, I need to pick my second and third priority. I have a carbon connected to an O, two O's. So a carbon connected to two O's versus a carbon connected to three O's. So definitely this is going to be my second priority, and this is going to be my third priority in there. So my priorities are 1, 2, 3, and 4. Notice that 4 is not behind. So I have to switch a priority 1 with a priority 4 to make 4 behind. The easiest way to do it is simply by putting the priorities like this. So I have priority 2, I have a priority 3, I have a priority 1, and I have a priority 4, which is in plane. So what you do over here is you switch, always switch, and then invert. So when you switch, it's going to be now your 4 here. Your 1 is going to be in plane, but don't forget that you switched, because you would need to invert right away after you figure out the configuration. So now I'm going to go by 1, 2, and 3. You pass by 4. 4 should always be behind. So when you do the configuration, you go along 1, 2, 3. passed by 4, you don't care about it because it is behind. This is a clockwise, so it is an R configuration, but in reality, it is going to be an S and not an R because you inverted. So here you invert. So what you do here, you do the invert. And now instead of being an R, it is going to be an S configuration. So again, what you do is you switch the groups, make sure that priority number 4 is always behind, do the configuration, do the rotation, whatever you get, you just go ahead and invert that or reverse it. And then that is going to be your actual configuration of that carbon. So now my configuration, which is the absolute configuration for this chiral center, is going to be an S configuration. As we mentioned, double bonds is whenever you have two, meaning that the carbon needs to be connected to two carbons and this carbon is connected to two carbons in there. And these are the carbons of the double bond. So this carbon is connected to two carbons. And this carbon is connected to two carbons, which are this one and this one. So in reality, a carbon double bond carbon looks like this. A carbon a triple bond carbon, meaning that every carbon is connected to three carbons. So this carbon over here, which is over here, needs to be connected to three carbons. So draw the three carbons in there. And then this carbon, which is this carbon here, is connected to another three carbons. So draw the three carbons. This is 1, this is 2, and this is a 3 in there. Same thing for the nitrile, C triple bond N. So the nitrogen is connected to three carbons, and the carbon here is connected to three nitrogens. So the carbon is connected to three nitrogens, and the nitrogen is connected to three carbons. This is 1, this is 2, and this is a 3. Those groups you are responsible to know. So you're responsible to know how to set the priority of triple bonds, whether it's an alkyne or a nitrile, for alkenes and for carbonyls, whether you're working with aldehydes, ketones, or carboxylic acids. Okay. Let's have another example in here. So we have different molecules, and the question is locate the chiral center and then figure out the configuration, the absolute configuration around the chiral center. So for the first one, the chiral center is here. For this one, the chiral center, you do have a chiral center here and the chiral center there. Again, chiral centers, these are centers that have 4 different groups. For this carbon, you do have 4 different groups around it. You have a CH3. Don't forget that you have a hydrogen. Every carbon is a tetrahedral geometry. And if it's a tetrahedral geometry, then if you have 2 bonds in plane, then definitely the hydrogen here is going to be behind because the CH3 is in front. You have these 2 bonds are in plane. And then you have this carbon over here to be a chiral center. You have this carbon to be a chiral center, and you have this carbon to be a chiral center as well. So all of those are chiral centers. And then for this molecule, this is going to be the only chiral center in there, where the hydrogen is going to be behind here. Let's always locate your hydrogen where it is. So the hydrogen here is in front. Here the hydrogen is behind. Okay? In there. And then here the hydrogen is behind. When the hydrogen is behind, it is easy when you are doing the configuration. So look at your chiral center in there. And then we're going to look at the groups that are connected to the chiral center. So you have an oxygen, you have a hydrogen, you have a carbon, and you have a carbon. Those 2 carbons are a tie. Then you look at the carbon, 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 carbon. It's also a tie. Then you look at the carbon, carbon, and carbon hydrogen here. Then definitely it's going to be a higher priority. Now between carbons and oxygen and hydrogen, the OH is going to be the highest priority. So that is going to be priority number 1. This is going to be priority 2. This is going to be priority 3. And that is going to be priority 4. And since priority 4 is behind, I don't have to worry about inverting or doing anything or switching the groups because priority 4 is already behind. So I'm going to go now by 1, 2, and 3, and that is counterclockwise. It's an S configuration. I keep it an S. I do nothing. You don't invert that because you did not switch the groups. So this is an S configuration. Let's have another example here. This is a CH3. This is a CH3 as well. Okay, and let's go ahead and set the priorities. So 4 is priority, hydrogen is priority number 4. And then see what I have here. On this chiral center, I have a carbon that is connected to, this carbon is connected to 2 carbons. So this carbon here, let's highlight it. So this carbon here is connected to 2 carbons. This is 1 carbon and this is another carbon in there. Versus this is a carbon that is connected to a hydrogen and to a carbon. So definitely this side is going to be a higher priority than this side over here. So this is going to be priority number 1. This whole thing is going to be priority number 1. This is going to be priority number 2. This is going to be priority number 3. 4 is already behind, so I don't have to do anything other than simply doing the rotation. So I'm going here by 1. You start with 1, 2, and 3. And this is clockwise, so you do NR. So the absolute configuration of the chiral center is NR configuration. We do the same thing for this carbon. Let me go ahead and draw it again. So we're going to go ahead and draw that again. I have my hydrogen here, my CH3, and then the CH3 and the hydrogen. So for this chiral center here, let's put an asterisk. That is connected to what? It's connected to a carbon that is connected to 2 carbons. It's a branch here. So it's a carbon with 2 carbons versus a carbon with a hydrogen and the carbon. So definitely this one is going to be a higher priority. So this is going to be priority number 1 over here. Priority number 1 is all on this side. And then I have priority number 2 on this side over here. And then I have priority 3 and I have priority 4. Now notice that priority 4 is in front. Okay, so since the priority 4 is in front here, I need to go ahead and switch. So we're going to go ahead and we're going to switch. And when we switch, then in this case, the CH3 is going to be, or let's go ahead and keep it like that. And the CH3 is, there you go, is going to be in the place of the hydrogen. So the hydrogen now is behind and the CH3 is going to be over here. We're going to keep everything the same for the other chiral center in there. And then I know the configurations here. Let's write them down. So that now this is the 4, this is the 3, this was the 1, and this one is the 2. And I'm going by 1, 2, and the 3 like that. And this is an S configuration. So all what you need to do is invert. And when you invert, then the S changes to an R. So now this guy over here is going to be an R configuration. So I had my first chiral center here to be an R. and my second chiral center here to be an R as well. For this example here, this is going to be my CH3. Hydrogen is already behind, so this is priority number 4. Now around the chiral center, what do I have? I have a carbon connected. This is a double bond, right? So this carbon is going to be connected to 2 carbons, but this carbon over here is connected to just 1 carbon. So definitely this is going to be a higher priority. So it's going to be priority 1. This is going to be priority 2 over here. And then this is going to be priority 3. And I'm going by 1, 2, and 3 like that. So this is going to be an S configuration, and it stays an S configuration because I didn't do any switching of the groups. Over here in this example, I have 4 chiral centers. So let's go ahead and do the hydrogen. So I have here a hydrogen that is behind. This is easy to find the configuration. So bromine is going to be priority number 1. This whole group here is going to be priority 2. Why? Because this chiral center is connected to a carbon with a chlorine versus a carbon with a hydrogen. So this is why this is a priority 2. This is a priority 3. And the hydrogen is a priority 4. And I am going by 1, 2, and 3 like that. And this is going to be an S configuration for that chiral center. Now for the second one, this is going to be my hydrogen, which is in front. So here, this is a priority group number 4, which is in front. The chlorine is going to be priority number 1 for that chiral center. And then number 2 is going to be on the side, and number 3 is going to be on the side. So this is going to be 2 over here. I'm using the green color for this one. And then this is going to be 3. So let's write it down. So I have my chiral center. I have priority group number 1, which is behind. Let me put it behind. So this is the chiral center, priority group 1, which is behind. I have priority group 4, which is in front. It makes it easier to draw it like this. And then priority group here in plane, and the priority 3, which is in plane. So we're going to go ahead and switch 1 with 4. So switching 1 with 4, now 1 is going to be in front and 4 is going to be behind. We're going to keep 2 and 3 the same. And we're going here by 1, 2, and 3. So that is an S configuration. This means that this guy is going to be an R. So this one is going to be an R. And then we have this chiral center over here. Since we're not showing the stereochemistry of this one being in front or behind, I'm just going to assume that it is in front to make it easy and make the hydrogen behind. So now your priority in this case, they're going to be, hydrogen is going to be priority number 4. This whole group over here, I have a carbon connected to a carbon and a chlorine versus a carbon connected to a carbon and a carbon. So definitely this is going to be a higher priority. That is going to be priority number 1. On this side here, I have a carbon connected to a carbon that is branched off 2 carbons. Here I have a carbon, carbon, and the hydrogen. So this is going to be second priority, and that is going to be the third priority over here. So this group is the second, this group is the third, and I am going by 1, 2, and 3 like that. And this is an S configuration. We're going to keep it an S because we didn't invert. For this one, for the last one, we have this whole group to be the first priority, and then this whole group over here to be the second priority, and this is the third priority in there, and hydrogen is going to be the fourth. And I'm going by 1, 2, and 3 like that. and this is going to be an R configuration. So this carbon is an R configuration, this one is an S, this one is an R, and this one is going to be an S configuration. There are other examples in the practice sheet that I posted, so please work those out. Now, another thing is when you are working with isotopes like hydrogen, like the isotopes of hydrogens, like deuterium and the tritium. Tritium is going to be the highest mass number. Remember that isotopes, they have the same atomic number, different mass number. So now I need to go with the mass number here. And T has the highest mass number than the D, which is deuterium. So if I have an example like that, I have a D and the hydrogen, definitely the D is going to be higher priority than the hydrogen. And I always want my lowest priority to be behind. Your lowest priority is not necessarily a hydrogen. It can be any low priority group, like a CH3, for example, depending on what groups you have around the chiral center. So not always you're going to have a lowest priority to be a hydrogen there. So hydrogen here is not behind, so we're going to go ahead and switch those two groups. And after we switch those two groups, we're going to get a configuration, and then we're going to invert it so that you can get the opposite. And that will be the real configuration for that chiral center. Now, the S and the R, these are included in the name because the moment you write the name, if there's a chiral center, you need to write its absolute configuration. So here, by looking at the name, I know that I have one chiral center in there. If you want to draw this molecule, the first thing that you do is you simply draw it and neglect the chiral center. So you draw the 1-chlorobutane. So this is the butane. And on the carbon number 1, you have a chlorine in there. And on carbon number 1, you do have a bromine on the other end. But don't forget that it's a tetrahedral carbon to start with. So if you choose two bonds to be in plane, then one of them needs to be in front and the other one needs to be behind. Always start by making the hydrogen to be behind. Make it easy on you and see if you get the right configuration that you have here. If you don't get the right configuration, then you can reverse the groups. So here I'm gonna start by making the hydrogen behind. This means that the bromine is gonna be in front. Again, remember, every tetrahedral carbon needs to have two bonds in plane, one bond in front and the other one is behind. Now we're going to go ahead and get the configuration and see if we get the S one, the S configuration. So on this chiral center here, we have a chlorine and we have a bromine. Bromine is a higher atomic number, so bromine is going to be the first priority. Chlorine is going to be the second. Definitely the carbon is going to be the third, and the hydrogen is going to be the fourth. And I'm going here by 1, 2, and the 3. And that is going to be an R configuration. I don't want the R, I want the S. So all what you need to do over here is simply reverse the bromine and the hydrogen, as simple as that. So all what you need to do is simply reverse it. Now you have your chlorine, leave the carbon chain alone, and reverse the hydrogen and the bromine, and now make the bromine behind and the hydrogen is in front. So if you do this, then in this case, the configuration for this one is going to be around this chiral center. This is going to be priority number 1. This is going to be priority number 2. This is going to be priority number 3. And that is going to be priority number 4. See, 1 and 4, 4 is in front. So you reverse that. You simply switch those two groups in here. So hydrogen will be here, bromine will be there. If a bromine is going to be here, you start by 1, 2, and a 3, and this is an R configuration, but you invert it and it will become an S. So this is going to be our representation of the S1 bromo 1 chlorobutane. We can have two chiral centers, and every chiral center you have to indicate its rotation, its absolute configuration. So here, by looking at the name, I know that I have two chiral centers in there. So as I said, go ahead and draw the dichloropentane first. So this is going to be the pentane. On carbons number 2 and 3, I have my chlorines. So make the chlorines in front. This is carbon number 2 and this is carbon number 3. Make them both in front so that you can have the hydrogens at the back first. Here you go. And then do the configuration for each one. So this is going to be priority 1. This is going to be priority 2, priority 3. And I'm going by 1, 2, and 3. And that is an R configuration. So this is carbon number 2. Name that or number that. So this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5 in there. Okay. So carbon number 2 is an R, and I already have that. So I am good with the chlorine being in front. And carbon number 3, this is going to be priority 1 to change the color. So that is going to be priority 1. This whole thing is going to be priority 2. This is a priority 3, and you have priority 4. You guys, this is a priority 2, the whole group over here. The reason why, because this is a carbon chlorine versus a carbon carbon. So this is going to be priority 2, priority 3. And you're going by 1, 2, and 3. And this is also an R again. So you get on carbon number 3 another R. So you keep it as is. So the best thing, again, whenever you have a name, make sure that your hydrogen is behind. If you don't get the same configuration as whatever is written, simply reverse the groups between the front and the behind, and you should get the right configuration.